Thank you for the introduction and for the invitation to speak here. It's a great honor. It's only my second visit to Russia, and the previous one was in 1977. So it was.
Do you feel any difference?
Well, many more cars, right? The other one was in Moscow also, so actually I don't know. This is my first visit to St. Petersburg. Okay, so anyway, what I would like to talk about is on the links between geometric function analysis and the quantum information theory, which is like a relatively new field, so rather interdisciplinary field, related to the project of building a quantum computer, of course, which is maybe still decades away. But the story starts, okay, in a way, starts a little bit earlier. So the first thing which I will mention will be, how does this work? Will be on the mathematical side, and that's something that probably essentially all of you did hear about, and that's Dvoretzky theorem. So also on my previous visit to Russia, actually I gave 2 talks in Russian, but those were the only 2 talks I ever gave in Russian, and I wouldn't try now, so it would be too painful for me and for you, I'm sure. So Dvoretzky theorem says the following thing, that if you give me a number m, a positive integer, and epsilon positive, then there exists another positive integer depending on m and epsilon with the following property, that for every n-dimensional normed space, there is a subspace, which is 1 plus, or which is 1, let's say 1 plus epsilon Euclidean. So another way to phrase it is to say that for every n-dimensional convex body, there is a section which is Euclidean or spherical up to epsilon. Okay, and well, is this just to get my, did everybody see that here? Is there anyone here who did not? Okay, so let me check. Who did see this theorem in their life? Okay, it doesn't exactly add up, but close enough. Okay, so now, so what I actually prefer, this I will erase, but I will write another form which I want to keep for future reference, and this is what I call the Millman's tangible Dvoretzky theorem. So this says the following, that how should I phrase it? Okay, so let's consider an n-dimensional space, or maybe let me just make sure that I use the same notation. Okay, Okay, so let's say here n-dimensional space. Space with two norms. So with Euclidean norm which I denote just by single bar, and some other norm. Which is with two bars. Okay, so then let's assume that so notation, so assume, so given here, and here maybe denote or assume rather, maybe it's better. So assume that there is some degree of compatibility between the two, so that's let's say that this norm is less than or equal than some number b times the Euclidean norm, and let's assume that, well, and or rather denote in this case that m is equal to the expected value of the other norm, and here this is the expected value, I mean, on the Euclidean sphere. Okay, so sphere is defined by this norm, and then the expected value of the other norm over over that sphere. So now let's say that, so let epsilon be positive, and let m be any number that is less than or equal than some, how should I write it, epsilon square, then m over b squared, and I will throw in here another numerical constant, something like 1/10 or 1/3 or 1/100, but I will not specify. Okay, and then times n here, right? Then for most m-dimensional subspaces, the following holds, that for every x in subspaces, let's say E, well, I didn't name the space, so just spaces, for all x in E, we have a two-sided estimate, and then which way I want to write it, let's say the double norm is less than or equal than 1 plus epsilon times m, the usual norm, and greater or equal than 1 minus epsilon times m times the Euclidean norm here. Okay, so that's the concrete version, well, the tangible version of Dvoretzky theorem. And maybe a comment here is similarly for B-Lipschitz functions. Okay. So of course, if whenever we have such an estimate, then this norm is B-Lipschitz with respect to the Euclidean metric. But there are similar statements for B-Lipschitz functions. And then the intrinsic fact here was that here we say over R or over C, and actually in the context of quantum information theory is the complex variant, which will be important. And before, well, this work that I will be talking about, which by the way is a joint work with Guillaume Aubrun and Elizabeth Werner. So there were 2 papers in Journal of Mathematical Physics and Communications of Mathematical Physics something like about 2 years ago. So before that work, actually, this we realized that we needed this type of a fact, and also for Lipschitz functions, and this best dependence wasn't known for complex spaces. Strangely enough, it was known for real spaces, but not for complex spaces, because the usual proof that gave this best dependence for real spaces broke down in the complex case. Okay, so anyway, this is the version I will be talking about, and what I want to emphasize is that this is very concrete, because if you have a concrete norm space, then those parameters b and m are something that you maybe actually hope to be able to calculate. Right? In some cases it's very simple, in some cases it takes some work, but in any case this is something that's rather concrete. On the other hand, this is a rather abstract statement, so this is, well, a nice geometrical statement. However, it doesn't really give very concrete information. Okay, so the next part of the lecture is I wanted to introduce some notation and give some, well, present some concepts from quantum information theory. But I have no idea whether this is, well, I may be telling things that are very well known, or maybe not. So, okay, so basically, surely not. Well, most of those things are mathematically rather elementary. It's basically language. Basically, it's jargon, right? And not mathematically, they are fairly elementary. Maybe let's do it here. Let's do it here. Okay, so quantum systems, quantum states, and then operations, channels, and whatever, right? So this is just jargon. Well, with which of this will there will be some mathematical concept, and well, if you are a physicist, then it's sort of like you have, this is what you breathe with. Okay, so anyway, so basically, so what happens is that usually, certainly, probably everybody knows this, like when you have a quantum system, then usually it is described by the wave function. And wave function is usually a unit vector in some Hilbert space. So there is a vector psi unit vector, or L2 function, which of unit norm. So this is in some Hilbert space H. So this is Hilbert space. And this is in that context, it's necessarily over C. It's generally agreed that in order to get any meaningful physics, you have to work with complex numbers. So basically, the real variants are only toy models at most, right? So then another. So this is unit vector. So this is state of a quantum system. A quantum system, right? So typically, if you have a particle which has d levels, for example, then that would be a h equals to cd if d levels. The energy levels or whatever moment. Well, so the most famous are 2 levels, and they are called qubits. Right? Qubits, probably, did everybody hear about qubits? No? Okay, anyway, those are just buzzwords, right? Doesn't really matter. Okay, so here, so basically for the purpose of this talk, those spaces may be infinite dimensional, right, in principle. But for the purpose of this talk, there will be only finite dimensional Hilbert spaces. So in particular, this will be a finite dimensional vector, right? So this will be CD, right? And as it turns out, a more useful description of a quantum state, somehow more fitting with the in some cases, rather than looking at the vector itself, you look at the rank 1 projection, orthogonal projection, onto the direction of that vector. So this is here I should say, or rather, orthogonal projection onto C times psi. So this is, so the device, notational device, is this too low now? For people in the rear? Too low? Yes?
For me it's fine, but for people here.
With me it's okay.
Okay, so maybe I will write up to here, rather here, which is if you think in the linear algebra terms.
You can switch the boards.
Hmm?
You can switch the boards.
Yes. I want to fill this, and I want to save space, right? Be economical with space, right? And I am not tall enough to write above the bottom one, I'm afraid. Well, okay, I may try. Okay, so anyway, so what the physicists usually write, then usually, so maybe I will not somehow avoid using that notation. So instead of, when they mean a vector, they write it as this. So this is a vector. This is a cat notation. This is a Dirac notation. If you write something like that, then this means that you think of this as a vector. If you flip it over, then you think it as about this as a functional. So if you write psi this, then you think of this as a functional, which is row vector, right? And so here, if you write it psi times psi this way, then this denotes the outer product of a column vector times a row vector, which is a d by d matrix, which is exactly the matrix of that orthogonal projection. So I'm somehow, well, dwelling on this because it will be sort of difficult to avoid using this notation completely. Okay, somehow if you prefer the sort of more linear algebra notation, this would be like psi times psi, maybe star. So this is conjugate transpose of the column vector psi. So this is a vector, right? And so this is a rank 1 projection onto this direction. Okay. Okay. So those are. This is how one describes the quantum states. Well, defines the quantum states. Actually, it turns out this is not enough, and this will become clear. So maybe I will still write it here and then raise it up. Okay, maybe now raise it up and then completely raise up. So more generally, quantum states are mixtures of such. Are let's say rho such that rho is greater or equal than 0, which means positive, semi-definite, which one we write as greater or equal than 0 as a matrix, and trace of rho is 1. So those are trace 1 positive semi-definite matrices, and of course each of these is like that, and every convex combination of this also is a quantum state. So those are like mixtures, right? And by the spectral theorem, of course, every matrix of that form can be represented as a convex combination of such rank 1 projections, right? So this is the similar states, and then I will know this as D of H whenever H is the original space. So this will be the notation. Okay, so whenever I write D, I mean this set, right? So where does this set live? So this set lives in the space of, let's say, matrices which are D by D. But not only that, but also self-adjoint, right? So, or Hermitian, if you will. And this is a real vector space. Vector space of dimension. So here it will be D square, right? And actually, if we impose this additional condition here, then this will be a hyperplane of trace or hyperplane. So this is a hyperplane plane there. So somehow what I like to draw it is that this is the positive semi-definite cone, and then you have the trace 1 hyperplane and no color choke. Well, not a big deal, but yeah. So this is your D, right? Okay. So this is what? This is a convex set, right? More or less by definition, which is in that high dimensional space. So that somehow it immediately seems that to look at this from the point of view of functional analysis, or this geometric functional analysis, this type of tools may be just the right idea. Okay, so now let's move this up. Erase this and go further. Okay, so in this quantum information theory, those are like the objects. Those are the objects. Now, what maybe I should mention that those rank 1 projections. Okay, these are called pure states, and they are extreme points of the set D. So of course, so this agrees with the terminology in sister algebras, right? Where you have a sister algebra of operators, and then you have states on that sister algebra, like this, and then you have pure states, which are the extreme points. And in this case, those are just exactly rank 1 projections. Okay, so somehow the ideology in physics is that basically if you have a state which is a mixture with some weights, and then you perform a measurement, then the outcome of the measurement under some appropriate setting will be probabilistic in nature, and the probability of getting a given outcome will be the weight associated with that. Well, vaguely that's what it is, but this is not going to be that important in what I'm going to talk about. Okay, so this is the object. Now, what are the quantum operations? So quantum operations. Operations. So those are operations that can be realized that correspond actually to some physical processes. Well, that's the ideology. But mathematically, those are what is called completely positive maps. So in physics, it's somehow generally assumed that physical operations are those which are represented by completely positive maps. There is some argument about whether it's exactly, absolutely, well, or maybe not, but basically that's the prevailing belief, I should say. What I do? Okay, it's here. Okay, so now do I need to explain what that is?
Completely positive.
Completely positive maps. Okay, so actually I could avoid almost explaining, giving the definition, because we are not going to use the rigorous definition, but rather a concrete description. But it doesn't cost a lot. So first of all, what is a positive map? So positive map will be a map. Well, first of all, what kind of map are we talking about? Now our states are matrices, right? So basically, so states belong to let's say bounded, for starters, to the algebra of bounded operators on some Hilbert space, right? And then there will be operation which works from either on the same space or maybe on a different, two bounded linear operators maybe on a different space, let's say K, maybe the same, maybe different. So this is the initial state, this is the output state after the operation, right? You act on a system, it changes somehow. And so here we have, let's say, phi, capital Phi. Okay, and now positive, it means,
K.
oh, that's another Hilbert space. Another Hilbert space. It may be the same, right? It may be the same, may be different depending on how you set it up. Basically, it's, well, and the first approximation should be the same, right? Because, okay, and positive just means that it maps positive matrices to positive matrices. So positive means that rho greater or equal than 0 in the sense of being positive semi-definite implies that phi of rho greater or equal than 0. So that's what it means, a positive map.
Is phi linear?
Phi, yes, phi is linear, yes, linear. And then it's somehow naturally acts on self-adjoint ones, but of course then automatically extends to a map on the entire space of operators. So that's not an issue at all. And completely positive means that not only it's positive, but also if in certain sense you work not only with scalar coefficients but also with matricial coefficients, then it also remains positive, and formally it's expressed in the following way, that also for every, let's say, what is the letter that he didn't use, let's say k in n, when you consider a map phi, and here tensor product with identity, okay, on m k by k matrices, okay, then this is going to be naturally a map from operators on H tensor product ck to k to b into on operators on k tensor product ck. So the map is also positive. Okay, so this is somehow mathematically sort of makes sense, and I'm not going somehow for, well, on the other hand, if you haven't seen it, this is just totally incomprehensible. If you haven't worked with that, it's somehow what does it really means with those, what are those things, whatever. No, now what this is just usual tensor product of like vector spaces, and what it means when you take tensor product of two Hilbert spaces, then this means that you have an orthonormal basis here, orthonormal basis there. So orthonormal basis in the tensor product are the products of the respective bases, all product of respective bases. So somehow this is all is in there. Okay, but we will have a more concrete description of what this means really, right? It turns out that all completely positive maps actually can be described in a simple way, in several different simple ways, which were sort of discovered independently in the last, whatever, 60 years or so. And they are known by maybe a rich Stein spring representation, or maybe Krauss representation, or Choi matrix maybe. Okay, so those are the names which are connected with those different descriptions of what this really means more concretely. And this I will just say in a moment, so that when we get into applications, it will be very concrete. Okay, so maybe what are the examples of completely positive maps? So maybe let's where should I do it? Maybe here is a good place for this. So examples. So basically there are two easy examples, and then it turns out that everything else is sort of made up out of those two easy canonical examples. So one easy canonical example is the following, right? So remember, those operations, those things here are matrices, right? Here is a matrix. So this is a row, and this is phi of rho, which is another matrix, right? Okay, so one example, which is the following. So if phi of rho equals to let's say v rho v conjugate. Okay. That's not very hard to understand. Now, of course, this has to make sense, right? So here we are looking at the product of matrices, right? So for this to make sense, those operators have to work from so properly. So this v star v has to act from I guess h to k, right? H to k. Then v star acts from k to h, right? So now it's somehow, when you compose it, if you start with something, so if rho is something that acts on h, then this composition will be something that acts on k, right? And if you think of those as just matrices, right, then they will have to have the correct size. But so if this was like CD and this was CM, then those matrices have to be m by k here, right? And that's basically all that is to that. Now it turns out that if you defined a map in this way, then it's very easy to show that it is completely positive, and it's just a whatever. That's, if you have never heard about this, that's a good exercise to see how that works. Okay, so now there is one thing which I didn't say, which didn't emphasize here, but maybe it's a point to emphasize to mention now. Now, for this to have a physical sense, right, the states should be mapped to states, which means that the map should be trace preserving. So if you start with something that has trace 1, it should end up with starting with something that has trace 1, so this should be trace preserving. So here I should say somewhere that this is preferably trace preserving. Now trace preserving, maybe analytically, is not a very how am I doing? Is something that is maybe not most natural. What probably you are familiar with is the Unitl map, which is the map which preserves the unity of your Banach algebra or sister algebra, and that's just the adjoint. If you have a map which is Unitl, then when you take the Banach space, so to speak, adjoint of it, you get a trace preserving map, and vice versa. So that's pretty much the same. Okay, so that's one. Property. So now where does trace preserving fit into this picture here? So that it's somehow it's another exercise that this is completely positive no matter what V is. But in order for this to be trace preserving, it is necessary that V is an isometry. V has to be an isometry. Okay, so V or V star. Well, okay, let's just, I think V, but we'll see that. We'll see that later. So V or V star has to be an isometry. Yeah.
H and K have the same dimension.
No, it not the same dimension. It may be isometry into. It may be an injective isometry, right? Which way? Probably V star, but okay. It will be more clear on the examples later. So, okay. Now, what is the other canonical example? So the other canonical example requires somehow looking at tensor things. And so this is so basically it's the following. So suppose that you start from a space which is a tensor product of two spaces, right? So we start with, let's say, H tensor product with something different. So you have a row which belongs to, well, let's say states on that. Okay, and then what you do is you apply what is called a partial trace, and I will somehow explain what that is. So this is, so row goes to the partial trace, so you trace over E row, and this is a state on the first factor H. Okay. Now, what is that? That's actually something very simple, which is the following: that if you think what is the partial trace? Partial trace works in the following way: that whenever you have a state which is row tensor sigma, so here you are in a product space, so operators are also tensor products of operators. Not necessarily products, but there may be mixed terms. So partial trace with respect to the second system, so this is in D of H, and this is in D of E, or more generally maybe in B of E, right? Just any operators, right? So this equals, by definition, what you do is you trace the second factor, trace over sigma, over the second part of, well, let's just take trace of the second factor times rho. Okay, and then by universality of the tensor product, this can be extended to a linear map on all on the tensor products on the tensor product of those two spaces, right? Whatever. So basically that's how it is defined. Okay, now as it turns out, when you combine, so this is also completely positive, which is not that difficult to check. And as it turns out, every completely positive map, and certainly trace preserving with some restrictions, can be expressed by a composition of those two, right? So now we're going to get into the concrete descriptions, right? And that's in the up to the change of notation and something like that. This is either Steinstrick representation or Krauss representation or a restatement of choice theorem on completely positive maps. Okay, so basically, so now what they really are. So maybe I think I skipped a couple of pages somewhere. Oh, maybe here. Okay, so I want to, so this is a general form, pretty much general form of maps, of completely positive trace preserving maps on B of H. Let's say it equals to B of CD to be on the safe side. So in this case, we assume that this is image and range are the same, just to simplify things. So the general form is the following: that first, consider let V from H, should I say it this way, into H tensor product with Z. B, maybe I will write here in CM. Did I have some CK? B, an isometry. Okay, and well, you should remember that H is really CD, right? So this is just a little bit of a complication. And then, so maybe I don't need a 1, right? Then and phi of rho equals to the following thing that I have it. So what you do, you take here rho. Okay, maybe I should state it slightly differently. So let's say psi be in H, right? So this is just a vector in CD, and rho equals to this psi, right? So this is the rank 1 matrix, which is the projection onto psi unit. Okay. Then what we define that phi of rho, which remember here is psi. So this is going to be the following: that you take a vector. First of all, we take a vector which is represented by V psi. Okay, so let's think this was a vector in this first factor. Now V psi will be a vector here, right? So now we are taking the orthogonal projection onto that psi. So actually the way it will be written by here, right? Because that's right. And then, so now what is this? This is a rank 1 projection in this space, right? And now we take the trace, we trace out the second factor. So we take the trace out with respect to this CK, which in physics they say environment of this. So now I define this only for rank 1 projections, but then of course by linearity this extends uniquely and canonically to an arbitrary matrix. So I could just write here a general rho to begin with, right? So maybe I could just erase that part and then just let's forget about this and just let's put here rho. Okay. And now here actually you could see that because I assume that V was an isometry, right? then V psi was a unit vector, right? Unit vector. So this actually, that product in the previous reincarnation before I erased it actually was a rank 1 projection of trace 1. So that was trace preserving, right? That was the crucial point. So this Bing isometry here gives the, okay, so I think it's a V, right? In this case, right? Okay, so this is, okay, and now basically the theorem is that if you have an arbitrary completely positive map, that it can be really represented in this way, right? For some k not exceeding d. For some k less than or equal than d. And actually one may just as well assume that k equals to d, because, well, if not, then you just embed it in a larger space and it's fine. Okay, so where are we here? So do we need anything here? Okay, so now what we have is we defined. Am I doing about half of the time? Yeah, about half the time. So we are almost done with introducing the notation, right? So now after basically one may start asking questions about this, about those objects, and so and then it will turn out that some natural questions in this quantum information theory reduce to very natural questions in functional analysis, which you can understand even if you didn't understand. Well, you still, it has to be, it will be, at some point it will be a statement about maps which behave like this, right? There will be completely positive maps in the hypothesis, right?
Where is the information in there? The term information figures in what you...
Oh, well, information basically is this, that, well, okay, so I can, I can say a few words about this, because what are the classical counterparts of those? Classical counterparts, so okay, in order to see the classical variant of this, you look at diagonal matrices. So if you look at the diagonal matrices of trace 1, those are just probability densities. So classical states, probability densities, or probability mass functions. Okay, so whatever corresponds to D, this script D, right? That will be the set of densities on, well, n points, right? Which is the positive, which will be the n minus 1 dimensional simplex, the positive phase of the ball in L1n, right? What will be the completely positive, the operations? So operations are stochastic matrices. Okay, so which means non-negative matrices, so that every, I guess, column adds up to 1, or maybe row, whichever way you represent them, because it's yeah. So this is the sort of the exact correspondence. Now so now what is a channel? Stochastic matrix represents a communication channel in a way, because if you think that there is, well, that you have, well, ideally you have identity channel which just sends you something to the, well, identical image of it, more or less, but usually you have some noise. So you have a stochastic matrix, and you get, for every symbol, you get some probability distribution in the output alphabet. And so that's where, and there you have information. Then based on that, you build Shannon theory, whatever. You define capacity of a channel. This is a channel. You define capacity, then you design codes to define capacity of a channel, and then there is Shannon theorem, etc., which gives a formula for with mutual information and so forth, and all of those have correspondence in that theory, corresponding ideas in that theory, and I will not really go into really that part, and moreover, for one reason is that I don't know that part very well, but anyway, it would I could spend whatever a semester, right, talking about that, even though I don't know much, but well, I know more about classical information theory, but in terms of giving a course, but okay. Anyway, so this is what that would be. So in that case, one defines the important concepts are like the channel capacity, for example. Okay, and this is something that I wanted to say about that. There is also a concept of channel capacity in the quantum context, but actually there is not that one concept of capacity. There are many concepts of capacity because it depends what kind of information you send out through this type of a channel, right? Basically, somehow physically, this is supposed to be the following: that you get there is some physical apparatus, or that you enter some bunch of particles in certain quantum state, you perform some operation, and you get maybe the same particles, maybe somewhat different because you may discard some of them, for example, and or so forth, in some different state, and you want to extract some features of whatever you want to do, right, from what you obtained, right? So this operation phi corresponds to some physical operation that you perform on that system in principle, right? So now what about capacity? So I'm not going to define capacity so what the capacity that appears here, irrelevant to what I'm going to talk about, is the classical capacity, which means that you have a quantum channel, which means whatever it means, right? Quantum channel will be such a map, right? And the question is, how much classical information can you transport using that quantum channel, whatever that means, right? In this case of stochastic matrices, it's sort of pretty clear what that means, because if you have identity matrix, which is d by d, then you can send a string of length d, right? So you can send d bits, right? If you have noise, then maybe less, right? But that sort of makes sense. Here it's sort of less clear what the sense is, but it's still there will be a mathematical problem which I will now state that is related to capacity of those quantum channels. So this is a so basically one somehow defines capacity of quantum channels, or even capacities channels. So the capacity that will be relevant here is the classical capacity, which means that you have a string of bits 0, 1, 0, 1s. You want to send it through your channel, possibly with multiple applications of that, using it many times. Okay, and the question is how efficiently you can do that. So basically, you somehow encode your string of 0, 1s into the original system of that you have to begin with. For example, if you have well, I don't, which is this spin up or down. You have n particles which are possible to be spin up or down. Then you can encode zeros as spin down, 1 and spin up. If you were able to send them those particles without errors, at the end you could read it, and you would be able to send whatever the number of particles, that many bits you would be able to send, right? And that would correspond to the identity map. This map would be the identity, which sends row to row, right? So every vector sends to another vector. You would be able to ideally read it. Of course, well, this is, well, particularly in the quantum world, there is, it sort of almost never happens that you can send things ideally. There is always some kind of loss. Okay, so capacity for quantum transport, so in particular classical capacity. Classical capacity. And this was essentially defined, this was essentially work by Cholewo, whom probably you know, right? Alexander Cholewo. And then there were like Westmoreland and Schumacher. I'm not sure if I'm not misspelling the names, so I am writing illegibly so that this will not be used against me in the recording. Okay, so one somehow defines, there is a formula. Okay, and now there is a question, there is the following question. So suppose you have two channels, or even phi and psi, two channels. Okay, so you can use them in parallel, and this corresponds in the formalism. This is the product channel. The product channel. Okay, and so here we have the capacity. Let's say call them C of phi, C of psi, and this just means how many bits of information on the average can you send by single use of that channel. So then, okay, so this is defined sort of by some kind of a limit version that you can use it n times when r is large. So then how many bits you can send by using it n times, and then divide it by n. You send and receive, right? How many bits? Well, I mean, reliably send to the other party, right? Yeah, okay, yes. If you don't care about receiving, sending is very easy, right? Yeah, and so that's basically somehow how the definition works, that you are allowed to use it many times, and then you divide it by number of uses, and how many bits per use, that will be a number. Ultimately, that will be a number. And the same thing for the other. And then the question was, is it true that if you use two channels in parallel, then this is the same as the sum of psi. Okay, so this was the question. Now, what is sort of trivial, right, is that it's greater equal. Because this is essentially, the reason is the following, that how do you send information? You come up with some kind of an encoding, which means that your string of bits corresponds to some vector in the domain of here, basically, right? Each possible string corresponds to some vector vaguely, right? And so you can just, and on the other channel also the possible string corresponds to some vector. So you just take whenever you have a string, you split it into two pieces. The first part you encode in here, the second part you encode in there, you send the product, and it's easy to well, it's an exercise, of course, which of course depends on the definition of the of the capacity, but that you get, at least you can by using them in parallel, you can, if you sort of use them independently, don't look at the interaction, then you can send at least as much, right? And the question was open for something like maybe 15 years or so, until a few years ago, was whether it's, you also have the estimate in the other direction. And well, then the answer turns out to be no. And however, before maybe I should keep suspense for some time. Yes?
Is it somehow simpler if phi and psi are the same?
Actually, it was known even before it was solved that the problems are equivalent.
Okay. And
If
then
you
the quantum capacity you mentioned, the VT is just the limit when we take tensor product.
well, of the same thing, yes, basically, right. Yeah. So there is what is called, there is some whole-level quantity, which is the single shot capacity, and then the true capacity is the capacity of the nth power of your channel divided by n limit, right? Okay. So anyway, but it's so here I'm sort of ready to state a mathematical question, which was known to imply this second inequality. Okay, so that now this was a work of several people, but it was terminated with a paper by Shor, who showed that true, by true meaning equality, if the following fact is true: if the simpler quantity called minimum output entropy is additive. Okay. Now I didn't define what the minimum output entropy is, but that will be the next step. So minimum output entropy. Did I have a notation for it? Probably. Okay, let's just say. So first I have to define entropy. So S of rho is trace of, minus, I guess, trace of rho natural log or maybe log to the base of 2. Okay, so this is if you know the usual entropy, then the usual entropy for probability mass functions is sum of pj log 1 over pj. Right? So here is the same formula basically, and this is the same as sum of lambda j log of 1 over lambda j, where lambda j eigenvalues of rho. Right? So this is the so-called von Neumann entropy. Von Neumann entropy. Okay, now so this is the entropy. Now what is the minimum output entropy? Is the following, that S min of phi is minimum or infimum over rho in, the all states rho, it will be clear where they belong, of phi of, S of phi of rho. Okay, so now so maybe a few like trivial observations about what this is, right? So the entropy, it's given by this formula. Entropy is 0 if your probability mass function is a delta mass functions concentrated on just one point. If you know for sure what the output, what you are having, if your random variable is constant, if there is only one possible value with probability 1, then your entropy is 0. There is no disorder, right? The entropy is maximal if all possible values are equally likely. If over some finite alphabets, if you have every value equally likely, and then it's equal to logarithm. Usually it's used with log to base 2 if you want to have bits. So then each of these is log of, there are n possible values, so this is log of n, and those add up to whatever the densities add up, 1. So it's log of d. So this is the maximal over alphabet of length n. The maximal value is log, let's say, to the base 2 of n, and the minimal value is 0, which is when you have one value for one of them, and 0 elsewhere. Now, similarly here, you get minimal entropy if your state is a rank 1 projection, because then it has one eigenvalue equal to 1 and the rest are 0. So which means if your state is a pure state. So pure states have entropy 0, which is minimal. And the largest entropy is the normalized identity. You divide identity by the dimension, then the eigenvalues were 1 over, well, for a space of dimension d, 1 over d, and you get entropy log of d. So this is something which is sort of pretty transparent what that is, even though this is not maybe necessarily something that one uses a lot in function analysis, but this is, it's sort of pretty clear what this definition means, right? And it's not that hard to start getting feel about it. So if the range, okay, if the range of your channel restricted to the states contains a projection, a pure state, then this is 0, right? If your channel sends everything to multiple of identity divided by dimension, which is possible, this is like the maximally mixing channels in a way, total noise, then this will be logarithm of the dimension, right? And now you're asking whether this quantity is additive under taking tensor products of your maps, right? So anyway, this is maybe not something that you would think about, not a question that you would think about when you wake up and have your tea or coffee, if you are a functional analyst, but it's something that you can perfectly understand and get even some feeling for it after you think about, you calculate some examples. Okay, so now, okay, so let us get, let us get to some maybe real translations. So to real problems analysis, which are even more natural than that one. So that I want to leave, so maybe I will erase this here. I probably need this one. So one elementary observation about this one is that about this function here, that this is a concave function, which is just follows from the fact that this is concave, right, for a single variable. And so this minimum is attained on an extreme point. And, well, I just erased it, I think, but extreme points of the set of states are pure states. So this is achieved on some rho which equals to psi. Okay, on some rank 1 projection. So you're really on a vector somehow in a way, so that okay, it will fit nicely into this picture here, right? Okay, so okay, so what? Okay, so the next step here. Actually, I will not really talk that much about this particular problem, but a slightly modified problem, but very closely related. And in order to, so what one defines is what is called Renyi entropy. So Renyi entropy, so actually p greater than 1, or actually different, well, and p different from 1, positive and finite, right? or maybe not even finite, P-Renyi entropy. And that's the following. So so what you do, rather than looking at the at this expression here, so what one does is the following: one divides SP of well, for whatever reason I have it sigma. There must be a good reason. So this is log of trace of sigma to the power p. So it's quite clear what this means, right? Because sigma to the power p, it's a positive. This is a positive semi-definite matrix, so you can raise it to the power p, which means you raise every eigenvalue to the power p, right? Then you take the trace, then you take logarithm of the trace, and then for good measure, you add a normalizing factor, which is 1 over p minus 1, or is no, sorry, 1 minus p. Okay? Which sort of, the purpose of this factor is the following, that as p goes to 1, then the limit quantity is this one, right? Okay, so now, so this is the purpose of this normalizing factor. But now look at this is even more interesting, because this becomes to have functionality meaning. And namely, I can write that this is the same thing as p over p minus 1, 1 minus p again, sorry, times logarithm of the Schatten von Neumann norm of sigma. Schatten von Neumann, or Schatten norm, right? Norm of sigma. Now, what is the Schatten norm of a matrix? Is that known to everybody? Yeah, okay. So this is, now it's sort of pretty much clear, because what is this thing here? This is the sum of pth powers of eigenvalues. Now we are talking positive matrices, right? So this is the pth power of the Schatten norm. So we take logarithm, p comes out here, that's it, right? Okay, so now the auxiliary question here is the minimum output Renyi entropy additive? So then you define S, let's say P, well, I have to write min here, is minimum. Maybe I should be more economical. This is space SP of phi is minimum over rho in D, whatever the space is, and then you say SP of SP of phi of rho is it additive? Okay, so that's a question. Okay, now why is it interesting? Because there are, well, this maybe seemed to, well, actually, first of all, this Renyi entropy often appears in information theory as some kind of a smoothening of the standard entropy, and has some interpretations. Also, for this particular problem, if we're able to prove this, that this is additive, then we get this just by passing to the limit, with p going to 1, because it's an exercise, because this is true, well, on each factor at the beginning and the end, so somehow it's easy to verify. So if yes, then the answer to this would be positive, and the answer to the additivity problem also would be positive. Okay, so now let's reformulate this problem still again, and this is going to be where should I do it? maybe let's try work here. Okay, let's try to use this somehow. So let's reformulate this. So now you notice here that that here this is we will be working in the range where p is greater than 1. So p is greater than 1. Then the Schatten norm is the true norm, right? Otherwise it's not a norm really. So that's the range we're working in. So for the purpose of that limit, this is limit p goes to 1 plus, right, from the right. So so now when we look at this, is what is this? This is, so now let's look at what we are really looking at. What we are really looking at. We are looking at minimum. Sort of forget about this factor, because this is for a given p, it's just a constant. The only thing we have to remember is that it's negative. So really the important quantity, which is somehow associated with sort of rephrasing of this, we may just as well look as the maximum over rho in D. Just forget about the log on phi of rho, P's norm. So there is a simple arithmetic relation, or algebraic relation rather, between this quantity and this quantity. Okay? Now, but now what you see what happens, you know that this one, both this and that will be obtained on the extreme points of the set of states, which is of rank 1 projections. And those are also extreme points, plus or minus that are extreme points of the trace class, right? So really this quantity here is the norm of phi considered from the trace class Schatten 1 norm to Schatten P norm. So we are able to interpret this quantity modulo this factor and modulo taking logarithm or exponentiating whatever as this norm. So really there is a relation between this quantity and this norm of phi as an operator between two spaces of matrices. Now since we are taking logarithm, we have a multiplicativity question now rather than additivity question. So the question here becomes question, do we have that norm from 1 to p of phi tensor psi is less than or equal, well, which is the same as equal, because greater than equal will be trivial, the norm of phi from 1 to p, psi from 1 to p. Okay, so at this point we have a clean functionality question. The only thing we have to know is that phi and psi are completely positive maps, so that's still, because if they are just any maps, this is badly false, which is maybe not that actually totally obvious, but not that difficult. Oops, getting messed up totally. Okay, so those are the dangers of working with chalk. This doesn't really happen with the beamer. Okay, so now, do I have any time left whatsoever? Okay, not much. Okay, so now let me try to connect this to Dvoretzky's theorem. Okay, so that would be, well, all that I will be able to do, right? So let's try to. Okay, so now. Is the answer no? The answer is no, and then the answer to this other problem is also no. So maybe here, so that I don't forget, this was obtained in 2008 and 9 by Hayden, Winter for the P entropy, and by Hastings for the von Neumann entropy. So even before, well, the question is whether is this good or bad. Now it's, on one hand, it's bad because the theory would be much simpler if this was true, right? On the other hand, it's good because this means that conceivably it is possible to send information much more efficiently using quantum phenomena. But for the moment, actually, the violation of additivity that one obtains from the counterexample is so minuscule that maybe it's, well, but this is maybe the okay, but maybe it's just because we don't know any better, right?
Is there any known bound, true bound with some correction here? It doesn't hold.
Well, actually, there is no dimension-free bound. In this case, the violation is really bad. There is, yeah, actually it follows from the examples that from this technology here. Okay, so now how is it related? So now let's try to connect it to Dvoretzky's theorem. So first of all, well, what is important is to remember this thing here, right? That how those maps really look like. Right? So we have to really work with maps which look like this. So now let's try to calculate some kind of entropy of this map is going to be if the map looks like this. So suppose that you have something here. So let's look at So the first thing maybe that I should emphasize, that if you look at maps of such sort, this minimum will be at, or maximum, whatever, the appropriate quantity will be attained in a pure state. So this will be really on a vector, right? This will be a real vector. So this is SP of phi of this 5 will be maximum of what you have to do here is you have to look at the partial trace with respect to the second factor here of V psi tensor V psi. Maybe I should write it this V psi star. Okay. Now, how does partial trace work? So now this is another exercise which is based on the following thing, that if you have a vector, so this vector here, remember this is in this product. This is CD tensor CK. Okay, so it's a tensor product of two. So there is an analog of the singular value decomposition, which is called the Schmid decomposition, which tells you that any vector, which maybe I will call, so let's call it phi, maybe lowercase phi. So phi can be written as sum of Si, or maybe Sj, U, J, tensor Vj. Okay, so this is the analog of the singular value decomposition for tensors rather than matrices. Every vector in here can be written in such a form where those are orthonormal bases, or orthonormal sequences at least, orthonormal sequences in the corresponding factors. Right? So if you singular value decomposition, every matrix can be written in such a form more or less, except that it's a slightly different. Okay. So now an exercise is the following, that if you apply this trace to the second part, then what does it really do? This means that if you have this type of an expression, right, then what happens when you look at phi times phi star? Then this is sum of j and, well, let's maybe use I and j this time. Si as j, and then I have u I uj star tensor vi vj star, and here I have to, okay, and here I have to apply the trace with respect to the second factor. So this carries over to here, to the trace here. And well, if this is orthonormal basis, then of course trace will be 1 if I equals to j and 0 otherwise. Right? Because trace, I can leave them around, and I usually move them around by the cyclical property of the trace. It's just, this is delta ij. Okay? So what I get here really is I get sum of sj square ui uj square. So what I'm getting here is I'm getting a diagonal matrix in the basis uj with those eigenvalues. Right? And this was a unit vector, so those things are add up to 1, which is what it should have been. Okay? So now let's go back here. We are looking so what is the maximum? Well, it will be here norm p, right? So because this was by definition maximum of the pth norm of whatever is the application to a state psi, it will be maximum over psi, norm of psi equal to 1, Euclidean norm, right? Okay, so now what am I getting here? So here I get a matrix, diagonal matrix in that basis with those eigenvalues, and now take a pth norm of it, right? Schatten pth norm of this. Now here I get a square, so what I'm going to get is I'm going to the square root of Schatten 2 pth norm of the original sort of matrix like this one. So this equals to the Schatten 2 pth norm. Is it squared or square root? No, it's probably squared, right? Of the matrix, which is sum of Sj and then Uj Vj star. So here I have a true singular value decomposition, right? I sort of flipped it from to the singular value decomposition. Now it's going to be, yes, I think square, yes, right. Okay, so now let's well, in the last couple of minutes, or well, actually I'm going over time. Now you see what happens here. What I remember, V was an isometry. Okay, so V psi phi equals B psi ranges over the sphere of VH. Right? What is this? This is like just I'm calling this W, and this is just a d-dimensional subspace of this space here, contained in C D tensor CK. Okay, so I have the following situation. I identified my map phi with a d-dimensional subspace of this space, which I am considering as the space of D by K matrices with the Schatten norm to P. Okay, so in other words, the last thing that is to be written here, maybe here. So what I'm looking for is the following. So let W be a subspace of M of D by K matrices. Okay, and we are looking at maximum of this quantity, right? At maximum over norms over vectors phi, whose Euclidean norm, or in this case it's a Hilbert-Schmid norm, so 2 norm equals to 1, of norm phi and here 2p square. Okay? So I'm getting sort of exactly this type of question like here. I'm getting a question. I'm looking on the Euclidean sphere given by the Schatten 2 norm, and I'm asking what is the maximum on that subspace of the 2p norm. P is some parameter greater than 1, so 2p, this is q greater than 2. Okay? So I am exactly in the problem, almost exactly in the problem of looking at this upper estimate in the Dvoretzky theorem here. So here this is the W subspace which corresponds to the C. Right? So now what happens is that this is really this was already, so our contribution was noticing that here one can apply Dvoretzky theorem, at least for the first, as far as the Rennes entropy is concerned. And when you just apply the Dvoretzky theorem essentially in the form that it was present for the Schatten classes, it was given as an example in the Figel-Lindenstrauss-Milliman paper in 1977, then you get that for as a function, when you apply it with epsilon equal to, let's say, 1/2, then you get certain value of the B. Here norms are totally explicit, so you know what B is. Actually, B is equals to 1 because it's this is the Schatten norm. 2p norm is smaller than 2 norm. Those are like little LP norms. Okay, so those are just numbers. This can be calculated. This follows from theory of random matrices. So all of this is totally explicit. You plug it back into the formula, and what you get is you calculated this quantity for a channel which corresponds to a typical subspace, to a generic channel in a way, to a typical subspace of your matrix space, right, which is identified with the channel via the formula here, right? And this turns out to be the harder part, to figuring out exactly they have it written anywhere. Well, I don't have it, have it written here, okay. So calculating this and this actually is the harder part. Estimating from below, this one is sort of easier, requires another trick, but it's just a half a page calculation. There is a way to estimate this from below that only depends on the dimension of the space that you get, right? So this is the connection which hopefully I managed to vaguely sell, at least, if not in technical details. Okay, thank you very much.
Are there any questions or comments?
Sorry, just a silly one about the variance. So, for a given subspace of the dimension D, we just compute this maximum, and then what do we?
So this gives us the right. Well, the other. Well, there is a little bit trick. What should be psi? So then it turns out that for psi one takes the channel which corresponds to the complex conjugate of that.
No,
in a sense.
That's probably a similar question. So, for any given W, what we have is the maximum of that norm.
Yes.
But then, should we minimize overall possible W's or?
No, what you see, in order to get a contradiction, right, you need to have one W here, another W prime there, right? If you are able to estimate this and that will be of the same form, well, it's like almost the same form, just some. There is a formula which connects one of them, so that and then you are able to calculate the lower bound on this one, because this formula there gives us an upper bound on those, which is as small as those things possibly can be. Right? That's what it turns out. Okay. And then it's relatively easy calculation to get a lower bound there, which gives a contradiction. But basically that argument there allows us to calculate, to calculate this quantity pretty much exactly for a large class of channels, and that's enough to produce a counterexample. Now the important thing here maybe to notice is that, to point out, is that the Millman's proof of Dvoretzky's theorem is probabilistic. So you don't really get an example. So it would be of great value to find subspaces in, say, for starters, D by D matrices of maximal possible or close to maximal possible dimension that are explicit, and for which this bound that I sort of hinted holds, but they are explicit. Now the same problem appears in the classical case for LP spaces, and this has, in that case, that's mostly for p equals 1 maybe, and that has that's related to compressed sensing. And there was lots of work, particularly in computer science, on getting algorithmically feasible ways of constructing such subspaces, and there is substantial progress there. But nothing that I really know of. Well, the only explicit examples are very, very far inferior to what one gets from this random example. And by comparison to the classical case, if those of you who know information theory, the original paper of Shannon calculated capacity by using random coding. And it took like something like 40 years or so that the code that one actually can construct are something like the 80% of capacity of the theoretical random codes given by Shannon. So, well, hopefully here it will be less than 40 years before we get somewhere. Since we know much more.
Some more questions. Well, then let us thank our speaker once again.